So, good night, everyone. How are you doing? Can you hear me? So, just leave a comment here that I just make sure everything's fine. Well, good night. My name is Monica. I guess you were expecting to see Juan or Bruno here today, but both of them had a problem. And I'm here to be your host. And I'm really excited because the topic today is going to be amazing. I'm a developer, so I don't know if my my point here is important because I'm kind of suspicious to say that I'm very, very excited for this talk. So, before we start, I just want you to know that if you have any questions, you can put the comment here, and later in the end of the presentation, we are going to answer some of the questions, okay? So, I'm not going to introduce Titus because this is a huge responsibility for me, and I don't even know how to start this. So, I'm just going to call him, and just a second. Hello.
Hello, you're far too kind.
How are you?
I'm very good, thank you. How are you?
I'm nice too. So thank you very much for being here today and bringing this nice topic.
My pleasure.
So I'm going to leave and the stage is ours, okay?
All right, thanks very much.
Thank you.
And thanks everyone for having me. It's for spending your evening or whatever time zone it is where you are. I'm gonna give a talk today on software engineering principles. These are sort of the major theses and themes in the book that I recently helped get put together and published, the Software Engineering at Google book, which I call the Flamingo book because of the O'Reilly flamingo on the cover. The talk should run maybe a little over half an hour. It depends on how chatty I get. If anyone has clarifying questions, definitely try to ask those on the chat, and hopefully someone will catch that and we can try to clarify. Otherwise, I will stick around for lots of Q&A at the end. As far as the talk itself goes, this is a talk that is very near and dear to my heart because it's sort of a derivative of the original pitch that I made to my VP here at Google on that sort of funded the Software Engineering at Google book as a project. So with no more introduction, let's dive in. So when we go out to customer visits or give conference talks, people sometimes come up to me and ask, so what's the secret? Why is Google good at software? And that, I think, sort of assumes that we are, and that is sometimes up for debate, but bear with me. I gave a talk a few years ago that included the following pitch. For the low price of only $5 million, I will sell you a tool that will enable you to keep your code and your developers and your engineers happy and productive forever. If everyone chips in, I will grant exclusive access to it and you can resell it however you like. And I think that this would be an amazing deal, right? Like, clearly, you all stand to make a huge pile of money reselling this tool, and I get to go retire to a beach somewhere. But no matter how many times I say this, no one ever actually reaches for their checkbook. Even if I was making a serious business pitch, nobody's ever going to actually buy such a tool because I think we all collectively have a very deep understanding that such a thing just can't exist. And why is that? And I think actually we've known this, there's been a hint of this, all the way back to Fred Brooks and the Mythical Man Month essays back in the 70s, 80s. There is no silver bullet. There is no one tool or language or engineering practice that is going to give us a 10x productivity boost. Instead, it's a continuous slow march as we refine our technology, our processes, the ecosystem, and our understanding of how it all fits together. We saw a similar thing with the SRE books, the Site Reliability Engineering books that Google also put out. It isn't just one thing that takes you from the bad old days of spotty uptime, low reliability, early internet, and gives you Google-style reliability and performance. Instead, there's a host of things that are necessary. You have to change the culture. You move to blame-free postmortems. It's not important to figure out who is responsible. It is important to figure out how it was possible to take the site down in the first place. You have to change the technology. You need monitoring if you want to run a reliable service in production. And even in how you conceptualize the problem. One of my favorite examples there is SRE talks about error budgets. And this is the idea that you're not aiming for 100% uptime for your service. You're aiming for some specified objective, some specified like 99.99% uptime. And then you use monitoring to monitor how much you have actually been up over the last 3 months or a year. And if it's less than that, then this means you have a budget to spend in terms of risk. You can deploy more features. You can push things more aggressively. And if you have spent more than that budget, if you've been down too much to actually hit that target, then you need to ramp back the risk. And when you make this seemingly very slight change away from we need to be up 100% of the time to no, there's a little bit of budget in there, then suddenly all of the incentive structures change, right? Dev and ops are working together. And this change in understanding the problem has widespread ramifications in how effective you are at actually doing the job. So taking a cue from the SRE book, I'd like to present our core tenets, the way that we frame problems that I think make software engineering as we understand it at Google different and effective. These are the main themes and theses of the Flamingo book. These are also, increasingly, the major sort of definition points of software engineering going all the way back to the early 70s. And the first major point here is a question of time. How is time going to affect your code, your project, your code base? What is the expected lifespan of the code in question? This is a really interesting and really important question to be asking. And it's really critical to realize that there are maybe 6 orders of magnitude of reasonable answer to this question. You could say, hey, how long is the code that you're working on going to last? And I could say, well, I'm just writing a little Python script. I'm just going to parse some logs real quick. I'll be done with it in 5 minutes and then probably throw it away. But it's also perfectly reasonable to say I'm committing a patch to the Linux kernel and it's going to be around for 20 years. But this question is not discussed. Some detail. So very often when a novice is learning to program, the lifespan of the resulting code is measured in hours or days. These programs and code snippets are often not touched again after their initial production. The whole point was actually doing the writing of them, producing that code. In some colleges, you might have a project course or a hands-on thesis. For most students, this is the only time that their code is likely to live longer than a month or so. And that short life expectancy for code doesn't necessarily change immediately upon entering the industry. A large amount of the software industry is focused on startups or app development. And both of these things have a notoriously short expected lifespan, usually between 1 and 3 years, depending on what stats you look at. Most of the effort at a startup focuses, by necessity, on keeping the business alive. The company might not live long enough to reap the benefits of any investment in long-term sustainability. And then, of course, there are all of the projects at mature companies that are just thrown away after a couple of years when they just become too bloated or unwieldy or the technical debt just overwhelms you. But by counterexample, successful industry projects and open source projects may have an effectively unbounded lifespan. You can't really predict an endpoint for the Linux kernel or the Apache web server. In most Google projects, we can't predict when we no longer need to upgrade our dependencies or language versions. These long-lived projects have a substantially different feel to them than programming assignments or startup development. Another way to look at it. On the short end of the spectrum, if I'm hacking on that Python script and a new version of my operating system comes out, should I stop what I'm doing and make sure that my script continues to work in the new operating system? I would say everyone agrees, no, that's silly. Finish your task, right? If you're only doing a 5 or 10 minute task, don't interrupt yourself to go upgrade your operating system. That's bizarre, right? Finish your job and you can upgrade when it's convenient. But there's a limit to when it's convenient. On the other hand, if you have code that was written 20 years ago, like Google pre-IPO, and we still haven't been able to update that to the current OS or the current version of its language or libraries, that's a really clear signal that something is wrong. Something's really broken there. And together, just these two endpoints mean that there's a scary sort of transition that happens in terms of the need to change. Somewhere around, I think, the 5-year mark, you start getting into, yeah, this really needs to be upgraded. And unfortunately, the cost of actually doing that first upgrade, the cost of paying down everything that is built up in those first years, is particularly challenging. And it's challenging for sort of 3 reasons, I think, each of which would be difficult on its own, but they kind of multiply together. The first of these is you're performing a task that hasn't been done to this project before. Googlers and some other people in the software engineering world talk about a thing we call Hiram's Law. That Hiram is one of the other co-authors on this book, and he describes it as for when you have a sufficient number of users, it does not matter what you promise in the interface, in the contract of your API. Every observable behavior of your API will be depended upon by somebody. And this is sort of challenging. Like anytime that you leave things totally stable, people are going to depend on both the things that you want them to use, the defined behaviors of your interface, but they also come to depend often just as much on the sort of accidental and side effect behavior of your interfaces. And this can be things like hash iteration, or do these results come back sorted, or all sorts of things. Like literally anything that you can depend on, someone is going to eventually depend on. And so by virtue of having left it stable for 5 or 10 years, you're going to have to pay down a lot of that sort of Hiram's Law cruft. A second thing that's costly is you're going to be doing an upgrade without experience or expertise. As an organization, by definition, you haven't done this upgrade before. And so you don't have policies and training and practice and experience to fall back on. So you're sort of making it up as you go. And as pretty much anyone can tell you, when you have to make it up as you go, that's higher cost for any sort of project. You're also, importantly, doing a larger than usual jump, right? You're probably going to upgrade from version 1 to version 5 to span everything from where it was when you started to what is current, instead of just an incremental upgrade from version 5 to version 6. And all of these, I think, multiply together. And thus, after actually doing an upgrade once or giving up partway through, it's pretty reasonable for a company or a team to overestimate the cost of upgrades and decide never again. And you commit instead to just throwing things away and rewriting, or just leaving things stale. But the alternate path requires you to not only get through that first process, but a second and a third, and get to the point that you can reliably stay current going forward. And this is part of what I call sustainability. Sustainability is the goal. For the expected lifespan of your code, you need to be able to change all of the things that you ought to change safely. And this is a subtle definition because it bundles in the expected lifespan of your code and the question of what ought you to do. And importantly, because it's dependent on the expected lifespan and the changes that you ought to make, it's really interesting to note that for very short-lived projects, you're sustainable by default, right? There's no changes that you ought to make other than the actual substantive like product design. Does it solve the problem that you set out to solve? It's only when you start getting longer and longer lived that you start having all of this extra overhead of all of the things that you need to react to, be they security bugs or upgrades or whatever. For these longer lived projects, making this transition to sustainability can be very challenging. It's also important to note that many developers have never worked on a sustainable project that recognized that it had a 5 or 10-year lifespan. So when someone like Google says, this is how we do things and why, a chunk of that will sound like utter nonsense, right? Why do you have all of these extra steps and safeties? You need unit tests and code review and design docs and static analysis and a million other things. Why do you have all of these extra hurdles. I just want to get my job done, right? From the perspective of someone that's only worked on short-term projects or projects that didn't achieve sustainability, their view is all of these steps are not necessary. They're not going to pay off. But I'm here to tell you that if you're on a long-lived and sustainable system, then you're playing a different game with different best practices when compared to a short-lived programming project. I also happen to think that most of these practices actually do pay off in the short term and will serve you very well if you grow. So in the same way that SRE pushes people to realize that error budgets are actually a better way to define the problem, software engineering is about realizing that the production of software is not the goal. Solving problems and keeping those working as long as is necessary is the real goal. And this is the first sort of major theme in our principles. Be mindful of time. Keep in mind this idea of expected lifetimes. Remember that with 6 orders of magnitude of how long this code might live, it's not the case that you have the same best practices on both ends of that system. Understand that long lifespans for software are rare, hard to plan for, and not well understood by most engineers, or by most programmers at least. But sustainable code is capable of change, and that's going to mean different things at different timescales. And it's often quite hard to get to. Now, the second point is about scale, and the question of when change over time has led us to growth, where do we start to fail? And in many discussions when we talk about scale in tech, we're talking about the sort of hardware scaling, CPU and RAM and disk and network resources. But the thing that I think is actually much more interesting is the question of how do your processes scale? How do your teams scale? How does the production and maintenance of all of the software that you're building actually work? As your organization grows and ages, are these tasks scalable? So for instance, when your project doubles in scope, you have twice as many lines of code, twice as many programmers, and you have to perform, say, an upgrade, like in the previous example, for a second time. Is that upgrade now going to be twice as labor intensive, or 4 times? Or can it be cheaper? Everything that your organization relies upon to produce and maintain code should be scalable in terms of costs and resource consumption. And everything that your organization is doing repeatedly should, in particular, be scalable in terms of human input. Time and scale come together in interesting ways. So let's consider what Google mostly learned about deprecation and churn many years ago. So traditionally, when we want to deprecate something, there's an old version that we've decided, well, we don't like that. It doesn't do all of the things that we wanted, or it has a bug or whatever. So we'd like everyone to use a new version instead. And one way that companies might approach this is to just ignore the existence of the old thing. But if we project this forward in time, right, we're thinking about time and scale. As new versions are introduced every handful of years, if you don't have a forcing function that actually pushes old and unmotivated users off of the old thing, then you're going to wind up with an ever-increasing amount of legacy versions purely for maintenance purposes and legacy purposes. And that may or may not actually be super expensive. It depends very much on what type of thing you're deprecating. There's a talk that I gave at CPPCon last year, which is sort of C++ centric, but I think the concepts apply pretty reasonably, where I point out the relative costs in maintenance for different things, for different things in the hierarchy of like higher level designs. So we have something like just a function, or a whole type, or a family of types, or higher and higher level things. And as you get up to the highest level things, then we start talking about the interaction of remote systems and microservices, your database structures, all of these things, right? And for introducing new versions of, say, just a function, you're not really going to pay all that much maintenance cost for having 4 different versions of a sort of similar function. On the other hand, having 4 different databases, 3 of which are deprecated, running in your production systems, that's kind of costly in the end, right? And so we probably want to consider some sort of method to push developers, to push teams off of those old systems, which will have some cost to it, but it might be less in the aggregate than the ongoing legacy maintenance for, say, 4 different database systems. Another thing that you can do, one way that we force people to do this, is to just force it, right? You mandate that everyone move off of the old system by Q1, right? By the middle of March, we're gonna turn down the old database. But this also doesn't scale, right? Because as your code base, as your organization sort of grows and expands, the leaf projects, the ones that no one else depends on, but that depend on all of the code in your, all of the code and all of the systems in your organization, the leaf projects have an ever-growing set of dependencies below them. And if every one of those dependencies has the right to say, all of our users, everyone above us in the dependency tree, must move from the old thing to the new thing by some date, right? Then you're increasingly forcing all of those leaf teams to run just to keep up. And even worse, every individual that gets stuck doing the work in those leaf projects has to learn all of the details of the task, right? They need to figure out, okay, how are we using the old thing? What are the differences between the old thing and the new thing? How do I actually switch over safely? And then execute that one time, doing a task one time, and then they probably didn't do a great job of it. It's probably very stressful and awkward. And when they're done, then they throw away all of the little bit of knowledge that they gained. As a large organization at some place like Google, if we rely on deprecation in this fashion, then we're paying that ramp up and throw away cost over and over and over again, hundreds or thousands of times. And if we do it to our external customers, it's even worse. And most terrible of all, in my mind, most of the projects that depend on whatever you're deprecating aren't actually leaves, because other projects depend on them as well. And this means that even the threat of, I'm just going to delete the old thing, I'm just going to turn down the old system, is a disproportionate threat, especially in a continuous deployment or trunk-based development mono repo sort of world, because you aren't just breaking the build of the project that didn't listen to your threat, you're breaking everyone that depended on them as well. So I imagine this with the analog of, hey, Timmy, if you don't put away the dishes, I'm going to blow up the city. This might get the dishes to be put away, but if it didn't, then either your threat was false, or you blow up the city and you're primarily harming bystanders that had nothing to do with putting away the dishes. I would argue that we probably can all agree, if your threat is primarily about harming bystanders, that's probably not the right policy. Sometimes, instead, we resort to heroics. Heroics don't scale either. Instead, at Google, what we try to do is we try to hold to the churn rule. The majority of the cost of any change must be paid by the team that is forcing the change. Right? There needs to be a published and reviewed transition plan. This constrains the designs for whatever the new thing is, but it puts all of our incentive structures into much more scalable places. And buried in all of this is a very important point, which is, practically speaking, policies like this scale better because learning takes time and energy. Knowledge and expertise within an organization have superlinear effects because they spread. And that is, when we make the team that triggers the change into specialists that understand how to execute it and all of the details and nuance, this is a much cheaper outcome, at least in a world where all of your users are visible to you. You're only going to pay the ramp-up cost a couple times, and then expertise makes things quicker and cheaper. In a successful organization, everything that must be done repeatedly must consume sublinear resources, especially sublinear human resources. This also applies to things like code base size and build test resources. The growth rate on these types of problems tends to be slow but steady. Pulling down your repo might take 30 seconds today and 10 minutes in 6 months from now. And an hour a couple years from now, right? And at no single point along the way is that like, oh, that's definitely too much. But in the end, when you compare 10 seconds to 10 minutes or or 30 minutes, it's definitely way too much. So you do probably want to put some sort of monitoring for your human processes to keep an eye on the things that are becoming really painful or becoming all-consuming for some poor heroic soul that is keeping it all together. Superlinear scaling for any cost is a serious problem for an organization. But on the flip side, the same properties of scale that make those costs dangerous make the hunt for scale-based efficiency extra potent. In a well-functioning organization, many tasks, especially those that are involved in sustainability that only become necessary over time, can be carved off for experts. Compiler upgrades and OS or kernel upgrades, API migrations. And the impact of those experts tends to be superlinear because of accrued expertise, automation, familiarity. When it comes down to it, you have to be aware of scale. You have to be thinking about this. Don't fear it, but respect it. It's a sign of success, after all. For another glimpse into how does this scale, consider version control policies and merging. It is not rare at all to encounter shops that have very strict policies about who gets to merge into trunk and when. I ran a poll on Twitter maybe 6 months or a year ago, and about 1 in 4 SWEs have had a regularly scheduled meeting to discuss which team gets to merge next. And it isn't really hard to understand why. You can imagine a team was off developing on a dev branch for a month, they finish, they merge, and now we find that the release is unstable. Everyone has seen this. Big merges can be costly. When you encounter a thing like that, you have 2 options. You either control the cost, lock it down, or learn to make it cheap. Practice, reduce the cost, not control the frequency. Make it common. And depending on the situation, either approach could be good, but for version control, the control the cost, lock it down approach is just bad. And the research increasingly shows that. Published research on trunk-based development leads to better outcomes suggests no long-lived dev branches, no choices where to commit, no choices on what version to depend on. And if you can achieve those properties, you're going to have much better outcomes. But you don't get that by default. You have to work at it. And I think that this is a perfect microcosm of what I mean by watch out for scaling problems. Companies that I was involved with before Google absolutely relied on this sort of merge strategy meeting with different teams and different contractors working on long-lived dev branches. At one point, we even had to hire an additional content management engineer to handle the load for merge and retest, because when we got to 200 engineers, the guy in charge of doing the merge couldn't keep up. And adding a second engineer to that didn't double the throughput on how many merges we could do, because the 2 of them had communication and coordination overhead, just as predicted in every engineering text for the last 50 years. Google, by comparison, has maybe a couple hundred times that many full-time engineers. Nobody is responsible for the merge. It just works. And it isn't that our engineers are that much better. It's that we spotted that this sort of policy wouldn't scale. It requires us to synchronize across all of the teams that are working in the code base. And we found something instead that required fewer decisions and, importantly, less communication and coordination. Another example of time and scale playing together is the idea of shifting left. In the past decade or so, an idea has emerged that has become a real common discussion point in software engineering and in DevOps methodology. This is the idea that shifting left makes things cheaper. The earlier in the software workflow that you can catch bugs, the cheaper they are to catch. And I see this as a direct result of thinking about these systems in terms of time and scale. Originally, this was phrased as shift left on security, because as an industry in the 90s and early 2000s, it was very common to see, well, and then we'll think about security once we've done all of the development, sort of tacked on to the very end of the software process. And as it turns out, that's real risky and expensive. Software that's already been released is constrained, it's hard to change, it's depended upon. Security bugs in the wild have legitimate real-world consequences, potentially up to the loss of human life. Catching those same bugs before that software is released into the wild is much cheaper. Users aren't depending on the feature. You don't have the same legal liability. You can fix it and try again. You might have to pay for more testing and maybe canary release costs, but it's still much cheaper. It would still be cheaper beyond that if you catch it in code review. The developer responsible knows what they were trying to do. It's already got the details fresh in their head. Languages like Rust even are prioritizing make it hard to even express the risky concepts, pushing the focus on security all the way back into the development step. That was also one of the major selling points for Java back in the early days. The same basic principle applies to bugs of all forms, not just security. If a bug shows up in Canary, that's a lot better than it being released. But now we have to look through all of the changes since the last release to see what broke. If we catch it pre-submit, we know exactly what broke. If we catch it during development, it might not even register as a hurdle during the developer's work. And as I said, I think this ties nicely to time and scale. Think of it as a time issue. Imagine building two houses. One construction company has alarms in place that detect when something was done in an unsafe fashion, and it sounds the alarm instantly. The other company has detection that is just as good, but the alarms only go off after someone is trying to move into the house. Which house would you like to buy? Heck, which house would you rather work on? It's also a scale issue, though. If we handle time perfectly and we move to a push on green sort of continuous deployment world where you submit a change, you run the tests instantly, and it's immediately pushed to production if the tests pass, it's still cheaper to find bugs earlier in the process because you don't have to worry about the question of, was this caused by me or someone else or the interaction of our two changes? So scale is the second really important lens when we're considering tools and policies and practices in software engineering, or anything really, but it is particularly acute here. And considering these ideas of time, which is how things will change, and scale, how your system will work as you grow, all that's really left is make good choices, make good decisions. If we understand that change must be possible, and we're explicit about the lifetime of the software that we're producing and maintaining, we understand the scaling goals of our organization and our engineering process, all that's left is to focus on making good decisions. People often say that everything in engineering is about evaluating our trade-offs, and I find that that is true even in software. The important thing is to make data-driven, or at least evidence-driven decisions, accounting for the realities and the requirements of time and scale. You need to aim for sustainability. You're going to make thousands of small decisions, but if they're done with a clear goal of sustainability for whatever the expected lifespan of your project looks like, then you're going to be in a better place. But you must remember, above all things, change must be possible, and that becomes increasingly critical the longer lived your code is. No superlinear scaling, especially for humans. And critically, because time and scale both have a tendency to sort of change our reasoning, you need to reevaluate from time to time. Context changes. The reasons and evidence that go into any given decision will change over time. A decision from last year might have been right, given the evidence available, but it might become wrong next year. It's reasonable to summarize all of this as make logical trade-offs. And in many respects, that shouldn't need to be said. Of course, you need to make logical choices if you want good outcomes. But this is less about a surprising insight and more about focusing on the underlying philosophy. Within Google, there's a strong distaste for because I said so. Inherent in all of this is the idea that there needs to be a reason for everything. Just because, or because I said so, or because everyone else does it this way. Those are the places where your bad decisions lurk. So what's the secret? I think it's these three things. Software engineering is not just programming, it's also time. And consider the impact of time. And I have just an endless bucket of stories that point out, like, the hard part in anything that we're doing is actually time. Be mindful of scale. Superlinear scaling is bad for any process that is required, committing your code, pushing a release, those sorts of things. Expertise and specialists can provide a similar superlinear impact in their domain if you have scaled up to the point that you have a scale. And make evidence-based decisions. Don't rely on because I said so. And remember that the evidence is going to change over time, so you need to reevaluate as needed. The book tries to tie all of these themes throughout all of the chapters in the book. This talk is basically chapter 1 of the book. The book sort of starts with the cultural aspects, the how do you work on a team? How do you lead a team? How do you make sure that your organization is, I don't know, doing the right things? Then we follow up with policies and processes about how to think about things and how to make your development, your engineering work smoothly. And then there's particular tools and technologies that we use at Google to make all of this work. And I will leave you with the idea that it's programming if clever is a compliment. It's software engineering if clever is an accusation. And if you understand just how deep that truth is, then you might be a software engineer.
Thank you very much for your talk. We have a question here. Just a second.
Right.
It's from Oliver. He said about the principle 1, time.
Right.
For software with a lifespan of decades, it's better to avoid newly launched frameworks.
Right. So I think this depends. One of the things, so I wrote the chapter in the book on dependency management, which is the idea of how you interact with code that your organization didn't produce. So probably whatever frameworks you're depending on. And one of the things that I really want us as an industry to get into doing is to look at what sort of stability that external code is trying to promise, right? And if it's a newly launched framework, I'm not sure that newly launched is so much the problem as have they said what their purpose is? So I come from a very C++ centric background. I served on the C++ standards committee for a while. The standards committee is really deeply committed to nobody will have to change anything when they upgrade ever, period. Like we have backwards compatibility as like a really deep commitment. By comparison, another very popular C++ library is Boost, which very explicitly does not promise any compatibility between versions, right? And so if you're building a very short-lived program, right, you probably want to use a lot of Boost, right? Because there's a lot of really fascinating, really wonderful sort of mad science things in there, right? But if you're building a really long-lived thing, you probably don't want to use Boost because you're going to have to upgrade, and they're not promising any smooth or attainable like transition from one version to another, right? And so I'm not sure that it's the question of how old is this framework. It's a question of what is the philosophy in the framework? What does the documentation say with respect to how are you going to change over time, right? If they are committing to no breaking changes, which is a whole thing, like that's sort of at least suggestive that they're aiming for you to be using that for the long term. If they're not saying anything, you probably want to ask before you try to commit to that in a very long-term project. As a side note, I totally hate the idea of like, what is a breaking change? Because literally everything is a breaking change for somebody. Hiram's law applies, and just a whole lot of, I could rant about this forever. But fundamentally, I don't think it's about the age. I think it's about what is the intent of that dependency.
Thank you. Yeah. We have another message. It's from Mateus. He said like it was excellent, and he said thank you.
Thank you.
For now, we don't have any more questions, but I have one comment. Like I was thinking about some projects that I worked before, and I saw that usually people don't think about these 3 principles that you said: the scale, the time, and the trade-offs. Sometimes people just want to like change everything because they want to try a new language or a new technology, and they don't think like, why are you going to do this? Like, it's going to be a huge difference. Like,
Right.
I don't know how to say this, but
No, you're absolutely correct. And it sort of, I think, gets back to like, what's the goal? What's the purpose in the software that you're producing? Like, if it's a hobby, if it's a learning project, if it's just a personal thing, then yeah, like rewrite it. Like the experience of scrapping it, changing it, refactoring it, all of those things, like those, it's really useful like practice and skills to have. But like, just because there's a new shiny way to do things doesn't mean you should change an old, like existing long-lived project, right? I'm not going to suggest like, I think Rust is probably a better programming language than C. I'm not going to rewrite the Linux kernel in Rust, you know? Like you have to have, you need to balance the trade-offs and evaluate all of these things. Like what's the cost? What's the benefit? Like, is this worth it? Can you even do it? And yeah, like most of those things don't matter too much for short-lived programming projects, but they matter deeply for software engineering projects, things that are going to last for longer and things where you have to interact with more people. There's a definition of software engineering that I've been falling back on a lot lately that goes back to the early 70s. And they say software engineering is the multi-person production of multi-version programs. And I think this captures exactly the themes in the talk here of it's about time, multi-version, and it's about scale, multi-people, right? And it's the communication issues and the scaling issues, the coordination, all of that. And it's perfectly fine to just be working on a programming project. Lots of things are just programming problems, but you need to be, what I'm arguing, I think, is you need to be aware of which thing you're doing. Both of them may be solved in an editor or an IDE with some code, but they're still different problems.
I agree.
Yeah.
So I was going to ask another thing, but we have some questions here. The next one is from Random Guy. Is there any tool do you use for generating the test classes and scenarios automatically rather than manually?
No. At Google, it is absolutely the individual engineer's responsibility to write tests that demonstrate that their code is actually correct. And a lot of people initially balk at that. They're like, I'm really good at this. Why do I have to prove that my code is correct? And they're, again, missing time, right? Because it is not like you're going to commit that test. That test is going to be constantly running. And it is not a proof that, I mean, it is a proof that your code is correct when you commit it. But more importantly, it is a proof that your code continues to be correct in the face of you have modified, you fixed a bug, everything else still works, someone else added a feature. Teams like mine that live at the bottom of the dependency stack changed all of your standard library and all of your utilities and changed the compiler out from under you. Does your project still work? Right? And so like it is very much on you to put in the tests that provide us that validation that like, yep, it would probably still be fine after I make this change. It is time consuming, but the important thing to remember is if you are a software engineer rather than a programmer, your job is not writing code. Your job is solving problems and keeping them solved. In which point, yeah, you're going to spend just as much time writing tests and, you know, fixing small bugs here and there as you are sitting down to write a bunch of code. It's less fun, but we're going to pay you for it. So, you know, it's a job.
Actually, I like to write tests. Like you said, I'm going to make sure that every scenario that I'm thinking it's like working. If someone else changes anything, I still have the documentation to say like, here we have to do this. Like, but that time we had to do this, but maybe the logic can change.
Yeah, for sure. Like my teams, we have a large mono repo my teams maintain a lot of the infrastructure, and we make a lot of changes. And our gold standard for can I commit this is not I ran your code in production. Like, I can't do that. Like, I don't know how to run your code in production. Right? Our standard for can we commit that change is do your tests still pass? If you don't commit any tests, if you don't provide us like good tests, we're just going to commit that. And if your code breaks in production, that's on you. So tests are not an option. Tests are a requirement.
And do you have like some process in the pipeline that check if the level of the coverage is correct, or do you have any step that someone else review your code and see
Yes.
your tests?
Yes,
Do you follow
mostly code reviewers. It's one of the primary requirements for code reviewers is to read through the tests and make sure that it's not just a couple simple example tests, but like you're testing the hard cases, and to make sure that the tests are clear and correct and all of that. It's not an accident that there are more chapters on testing in the book than any other topic by a significant margin. And then the second most common topic in the book by chapter count is code review. I think that's not an accident. That's very, very intentional.
We have another question from Dennis. He said, can you describe some experiencing with project that was not created with the culture for a long-lived project, but now it exists for many years?
So only sort of, and that's partly because like I came to Google after Google was already around for 10 years. So, I get stories of the earlier days, and everywhere that I worked before that, I was only there for a couple of years, so I didn't have the same sort of experience, and all of the things were much shorter lived. But one example that I could give, back in, say, like 2006 at Google, we realized we really needed to upgrade the C++ compiler. We had not done that ever. It was just the same version as whatever was checked in on some developer's machine back in like 2000. And there had been some fixes and there had been some advancements, and like we were kind of behind the times. But we also at that point didn't know, like we only had barely learned the lesson of you have to have tests. And we didn't have practice in executing like large scale refactoring and all of these things. So there were a lot of shortcuts that were taken back then for expedience sake, and like because no one had any real notion that it was going to be around for a long time or that it was going to, come back to bite us. And I joined up 4 years after that, and I started hearing stories about some of the things that we were like sort of fighting with by like 2011. So like 5 years after some of our like hacky things were done. And then in 2015, started a project that was paying down a lot of our internal technical debts. And it took probably 20 engineer years of effort to actually undo the like hacks that we had done in 2006, because we didn't know that it was going to be around that long. And the longer that you go, the more things depend on it. And like, it was really, really, really hard to unwind all of that. But having done it, now everything is so much cleaner, so much less that we have to train everybody in, like when they come start work there. So much easier to share code between our code base and other places. Like, it's well worth it, but it was a lot of work. And that was, I think, almost directly because we just didn't know that it was going to be that much of a problem or that it was going to be around for that long.
So. Okay. It took like a lot of people to solve this. It was a huge thing.
Yeah.
We have another question here from Álvaro. MDA is an old concept, but what do you think about the methodology in a way? Keep a pattern or structure over the source code lifetime? Do you know any actual company using it?
I don't know which MDA we're talking about, so I don't think I can answer this question.
Me neither.
Maybe.
Maybe Alvaro can send
Yeah.
another message explaining more.
Yeah. Yeah.
Okay. There are some people here saying that they missed the beginning of the talk. So the live is going to be like in the channel, so you can go and watch it. For now, we don't have any questions, but I have one.
Yeah.
Let's suppose like you are starting a new open source project. How do you know like how to balance all these three concepts, these principles? Because like in the beginning you don't have lots of people using, so how do you know how to change, when to change? Because it's really difficult to understand.
It is, and I think it again depends very much on what your goal is. Like, if this is just a personal project for funsies, then you're probably going to treat it more like a programming project. Like, it works in the version that it is. I'm not promising that it's gonna never change. Like, whereas if you really want it to be usable and in a fairly stable way, then you're going to have to put a lot more thought into under what circumstances are you going to make a breaking change? Like, how easy are you going to make that for users? What do you do about diamond dependency problems? It's a lot harder. Like, I think the example going back to Fred Brooks in the Mythical Man Month essays, he talks about the difference between, I forget exactly the terminology he uses there, but he's got like kind of a two-dimensional, like simple, like one version, like one person sort of project. Multi-version is much harder. Multi-version, multi-person is multiplicatively harder. And I think we need to get a lot better at being clear about what our intent is. Like, what are you promising? How do you want this to be used? And I think
It's not that easy to like each scenario is a case that we need to analyze.
Right. And there's no one right answer, right? Because like, I'm not going to say that Boost or the C++ standard library, that either one of them is better. So they're different tools for different purposes. Like, you have to decide what sort of tool, what sort of thing you're building first, and then let the reasoning flow from that decision, not the other way around. So.
Okay, thank you. Alvaro sent here a message. He said that he was talking about model driving architecture.
Architecture. So a lot of the parts of the world that I live in don't focus so much on big picture architecture things. So this is not an area that I am particularly familiar with. So I think I don't have anything that I could actually say intelligently here.
Okay.
I think what you're getting at, though, is and I may be totally speculating or maybe completely wrong, so take this with a grain of salt. But the model-driven approach is trying to give us this is the ground truth of what the code is supposed to do. And then when the code doesn't match what the model says it's supposed to do, then that's a bug. And that's okay, but requires us to have, in the first place, have produced that whole model and like verified the model and all of that stuff. And that has, I have not seen that take off. Whereas what we do see works pretty well is tests as a replacement for that model. And this puts, this tends to produce more usable interfaces and better designs. It is not provable in the same way, but the intent is not actually provable correctness. The intent is to find a good balance of how much signal do we get about, yes, this change is correct, yes, this change will be fine if we push it to production, without blowing way too much resource cost on the validation and the verification, and with it still being simple and approachable and easy to adopt. And we find that tests give us a very high cost benefit trade-off for those purposes. I think that gets at your point, but
yeah, okay, thank you. We have another question. Can you talk a bit about monitoring and observability as part of the software engineering culture?
Right.
I assume lots of devs are not used to think about monitoring when coding.
Right. So a different talk that I've been giving lately talks about the idea that your CI system is actually exactly the same morally as your alerting system in production. And we're looking at the same sorts of problems and taking the same sort of response. So in the monitoring and alerting perspective, you have some application specific data that you're exporting. If it's like a storage system, it might be throughput. If it's a video system, it might be like how long are people actually watching, how many videos are they watching in a row, how many kitten videos have been uploaded in the last 5 minutes. And then your monitoring systems are keeping track of those stats in production as they go, and when they fall out of some accepted range, then you fire an alert. Morally, this is exactly the same thing as a unit test, right? You are asserting this is my threshold for correctness. This is the value that I care about. If that falls out of this line, then we fail. And so your CI systems, Travis and Jenkins and whatnot, that are running your tests are firing off an alert in exactly the same way that your alerting system would be in production. We're just doing it earlier in the process and therefore cheaper. But they're morally actually the same thing in a lot of respects. And what I think is interesting about this model is you could, in theory, have no unit tests whatsoever and just have all of the same assertions from your unit tests exported as the variables that you're monitoring in production and have the same assertions in your production alerting systems, right? You just don't, because it's cheaper to catch all of those bugs earlier. And so when you start thinking about it in these terms, the devs that are not familiar with the monitoring philosophy, if they have some experience with unit testing, then you just need to talk to them about applying okay, you want good tests that are going to tell you is this change safe? Is it safe to push this code to production as it stands? You don't want tests that fail randomly, are flaky. Similarly, you don't want alerts that fire randomly, they're flaky. You want tests that fail only if there's actually a problem, not just because some thing that didn't matter that much changed. You don't want them to be brittle. They need to actually be high fidelity and actionable, which is the same for alerting, right? You don't want the alert went off because we passed some totally arbitrary threshold that didn't actually matter. The system was actually healthy. I just picked a bad threshold. right? But interestingly, the comparison goes both ways. So you can also take all of the, I think in some cases, higher quality published like philosophy around monitoring and alerting best practices and push that back into, and this is what you need to approach, like this is how you need to target your unit tests. And I think that comparison is actually really, really cool. I hope that gets to sort of what you wanted me to talk about there.
Thank you. Romulo just said that it was an excellent meetup, and he just bought the book today, and he saw that it has a lot of interesting
Great.
topics.
I hope you like it.
We have one more question from Dennis, and he said, do you recommend test pyramid to structure test coverage?
Basically, yes. The people that wrote the testing chapters have refined that a little bit. There's a little bit more nuance in there in the book. But basically, yes. Like, you want most stuff to be unit tests and a smaller number of things to be the higher, more expensive, less, more flaky, less reliable, like, but more real integration tests and end-to-end tests and all of those things. So yeah, I think it's a good place to start for sure.
I have a question, like in the team, how the analysis of the principles work. Like anyone can say, hey guys, I was like analyzing this project here and I saw that we need to improve the scale, or like how do you discuss this?
I think it's less formal than that, but it is the two things that come up most regularly are we're going to need the ability to change this at some point. And the amount that we're going to change it and the cost that we're willing to bear for changing it is going to vary from topic to topic rather significantly. One thing, for instance, a lot of the simple examples for Hiram's law and carving out the ability to change things goes back to hash table iteration, where it might be the case that in your programming language, you put 10 elements into a hash table, and then you iterate through them, and you get them back out in the same order every time you run the program. That might not be the case when you upgrade to the next version of the language, right? But if your tests depend on, I got those same things out in the same order, then your tests are going to fail. Or, unfortunately, if your production systems also depend on that, like, you're going to have a real bad time when you upgrade language versions. From our perspective, the problem is deeper because so much compute is actually burned doing hash table sort of operations. And so we really aggressively want the right to change our hash tables in structural ways or change to find a better hash algorithm. And all of it, like anything that you do to change those things, is going to change the order that the elements come back out. And so we've been aggressively trying to randomize the order, even just within, like, if you run the program twice, you're going to get a different order. And this is sort of a defense against Hiram's law, because if you can't depend on it, then you're not going to accidentally depend on it. And we have actually some success on this. We've changed the hash function that most of our common hashes rely on to something that's meaningfully more performance efficient just a couple weeks ago, and didn't break anything, which was kind of magic. I mean, it took us a lot of time to get to the point that we can do that, but now we have carved out that ability and can apparently just do that when we need to. So that comes up in topics where like, yep, someday we're going to need to change this, so we need to plan for that. Because if Hiram's law, I describe that as it's like thermodynamics, it's like entropy, right? You're never going to actually win. You can only reduce it, but you can make it easier, right? And that's important. So we have a lot of discussions about someday we're going to need to change this, or we need the right to change this. We need the capability to change this because the stuff that we're working on is going to be around for a long, long time. It's also pretty, it's not uncommon to hear stuff or people talk about, yeah, that's not going to scale. Even just discussions about like communications and things like that. It's especially troublesome inside a place like Google, where now we have, I don't even know, 50,000 engineers. Anything that requires a lot of communication, like if I have to broadcast this to everyone for this to be safe, I can't do that. Right? So you're going to have to find a different, more scalable approach. And the nice thing is, like, that's sometimes more work for you, probably less work for the company, but it's those solutions that don't require, broadcasting to 50,000 people are usually more reliable too. So,
Okay, thank you. So we don't have any more questions, and I'd like to thank you again for this amazing talk and also for answering all these questions.
Yeah.
And like for me, I would say that I had a great time and I learned a lot with you today. Thank you very much.
I'm very glad. Thank you so much, everybody. Have a great night.
Thank you, everyone. Good night. Bye.
Bye-bye.